Hello everyone. Thanks for your watching. I'm Yudi Zhao from Fudan University. I'm going to report our work on automatically detecting and exploiting template escape bugs. My talk is organized in parts. First, I will introduce some background knowledge. I will be referring to template engine as TE for the sake. TE is widely used in web applications to ease the development of user interfaces, such as PHP TE Smarty, Twig, Node.js TE EJS, Python TE Jinja 2. They help web applications generate dynamic HTML files from the template. According to our research, more than 65% of popular PHP applications on GitHub use TE to generate front-side files. How do TE work? TE render input data into HTML documents according to a predefined template. For example, if the template field is hello name and the name parameter is Bob, the TE will render the HTML page as hello Bob. This is a simple use case for the TE. Of course, the functions of the TE are not only this. TE usually provides the template code with rich functionalities. For example, Smarty allows a function tag to invoke the PHP function, but this powerful function also introduces new attack vectors for the TE, such as this picture. When attack captures the content of the template, he can use the system function to execute commands to attack the server side. We call this server-side template injection attack. Moreover, diversified attacks in TE also enable SSTI attack to achieve another exploit primitives, such as the location field include cross-site scripting, remote command execute. To prevent this hazard, many TE introduce Sandbox model to defeat SSTI attacks by restricting the TE capabilities. This is an overlooked TE bug that could empower an SSTI attack to bypass the sandbox and enable RCE attack again. We use this CVE as an example to introduce such kind of bug. Figure 1a shows a code piece of Smarty that translates the function tag in a template into PHP code. At line 1, the function name which defined in targ is used to compose the corresponding PHP function name. Later at line 6, the composed PHP function name is directly output to the PHP file, including another translated lines. By examining the code piece in figure 1a, we observe that the name variable at line 1 can be countered by an SSTI attack, and its value is directly output to the PHP file at line 6 without any synthesization. If the attack injects this code, we can observe that the final PHP file is transformed into this, such as executing system ID and enable an RCE attack. In this work, we want to conduct an in-depth study on template escape bugs to figure out 3 questions. First, what is the cause of the template escape bug? Second, how to automatically detect and exploit template escape bugs. Third, what is the severity and the prevalence of the template escape bug in real world? However, our study meets 3 challenges. Challenge 1. It requires a fine-grained analysis of the template input, because different TE have their specific grammar and it is hard to learn the syntax of the template input. Challenge 2. It requires a specific payload to track and exploit such bug. Only carefully constructed payloads could trigger a template escape bug, but synthesizing and exploit is also quite challenging. Challenge 3. There lacks an oracle for identifying template escape bugs. Even if an input successfully exploits a template escape bug, it is hard to judge whether the generated PHP file has been injected with the executable code. In light of these challenges, we propose a dynamic testing-based approach called TEFuzz. It is a testing framework for different TEs, and it can create test cases to discover and exploit template escape bugs. The design principles of TEFuzz is balancing exploration and exploitations, improving code coverage while avoiding redundant testing. First, let's look at some basic concepts. Test case. In TEFuzz, a test case is a piece of code in the format of the test TE. TEFuzz detects template escape bugs by testing and mutating test case. Escape point EP. Only a part of the template code will be output to the PHP file. We use an EP to refer to such a part of test case. For example, the value of the name parameter is an EP of the test case. Escape context EC. We refer to the code context of the EP in the output PHP file as the EC of an interesting test case. Interesting test case is a test case contains at least one EP. PoC, the test case that can raise PHP error. Exploit, the test case that can enable RCE attack. This is the workflow of the TEFuzz. Step 1, seed collection. Step 2, interesting test case identification. Step 3, PoC generation. Step 4, exploit synthesize. Then we use the TEFuzz to test and evaluate the real-world TE. To find the right dataset, we set 3 criteria to select a TE. First, we only consider generation-based TE. Second, it should be a popular TE. Third, the TE should have a sandbox model to mitigate the SSTI attack, or it should not support executing PHP code in the template. And we collected 1,728 test cases as the initial seeds from offshore documents and the testing field in TE's source code. Our evaluation answers 5 research questions. How prevalent are template escape bugs? How severe are template escape bugs? How does TEFuzz compare to SSTI scanners? How feasible is exploiting template escape bugs in real-world applications? How helpful are the internal design of the TEFuzz? For RQ1, we found that almost every TE has template escape bugs. In all, TEFuzz reports 135 bugs in this TE. The results shows that template escape bugs are quite prevalent. For RQ2, TEFuzz successfully exploits 55 bugs and generates an exploit for every reported bugs. Among all the TE in our dataset, only Twig has no exploitable bug. To our knowledge, TEFuzz is the first toy to detect and exploit template escape bugs, but we noticed an SSTI scanner named TPLmap, which claims to be capable of bypassing the TE sandbox. Thus, we conduct a comparison experiment between TPLmap and TEFuzz. Our experiment seeks to answer 2 questions. Can TPLmap discover template escape bugs? Can TEFuzz help TPLmap to discover exploitable SSTI vulnerabilities? First, we have enhanced TPLmap to support TE in our dataset. The results shows that TPLmap only discovers template injection points but fails to bypass the TE sandbox. Second, with the RCE payloads generated by TEFuzz, TPLmap successfully breaks the TE sandbox. In RQ4, we evaluate the feasibility of template code injection in the real world. First, we search known vulnerabilities. We search keywords in the CVE database and read security blogs and vulnerability reports. Finally, we find 5 vulnerabilities that use a vulnerable TE in our dataset and achieved full exploitation on all of them. Second, we want to discover zero-day vulnerabilities. We collect 18 PGP applications that use a vulnerable TE in our dataset. After that, we did two experiments. First, we used TPLMap, Cobbler, and TEFuzz for automatic detecting bugs, but unfortunately, we found zero vulnerability. Then we ran another manual discovery and found 6 vulnerabilities, as shown in the table below. With the exploits generated by TEFuzz, we successfully achieved RCE attack on these vulnerable applications. TEFuzz has introduced several important designs to effectively detect and exploit template escape bugs. In this research question, we measure how do this design help TEFuzz by reporting some internal results of TEFuzz. The results shows that these models help TEFuzz avoid redundant testing and detect real vulnerabilities. Test case adaptation and exploit synthesizes have also helped TEFuzz a lot. Test case fix rate is 69.4%. It helped to collect 6.7% more seeds, discover 21.6% more bugs, and synthesize 31% more exploits. Exploit synthesis model make 135 exploits, of which 55 ones are useful. We analyze the reason for the exploits. First, the payload used to drop the escape context in the PHP field make the TE fail to parse the template code. On the other hand, TE raise errors when checking the format of the exploit. Finally, I summarize our work. We study an overlooked and severe sandbox bypass vulnerability in TEs and demonstrate its root cause. We present an automatic tool to detect and exploit template escape bugs and introduce several new techniques. We discover 135 bugs in 7 PGP TE and construct 55 exploits that enable RCE attacks. Thank you for listening.